You got it.
So, as quantum hardware advances, the question becomes, how do we build applications at scale? Dr. Erik Garcell from Classiq will address the development layer, how we move from capability to deployable solutions, and how modern development platforms are accelerating adoption. Please welcome Dr. Erik Garcell.
Thank you, everybody. Now, just to get things started, a quick show of hands. Who here feels a little bit confused or intimidated about quantum computing? All right, good. I'm not alone. Now, I saw this wonderful introductory video from Nova documentary that I thought was just the most phenomenal. You are not alone in feeling intimidated by quantum computing. It started off with this Nova program contains scenes of quantum physics, which is known to cause confusion, anxiety, and even heartbreak. Please consult your local physicist if symptoms continue. So I will be your local physicist to help you guide through the eccentricities and confusions of quantum computing. And I work for a company called Classiq. We have a quantum software engineering platform trying to make quantum computing easier to use, deploy, understand, and make it so much more like computer science and standard programming than it is kind of this confusing topic of probabilistic bits and superpositions and all these aspects that really cause the not it phenomenon, I like to call when I go to businesses and I talk about quantum computing. The word quantum gets a lot of people to stand up in the room immediately and go, ooh, not it. Nope, get the technical person in the room who's a little smarter than me who can understand this. So we're trying to make this a little bit easier to understand, a little bit more dynamic and applicable. Now, Classiq, we're the largest quantum software company in the world. We closed our Series C funding round a few months ago at about a little over $200 million. Thank you also IonQ. They're one of our more recent investors. We also have investors like AMD, SoftBank, Libutan, the Intel CEO, well over 100 employees, global company, working with plenty of Fortune 500 companies, and I'll talk about that in a little bit as well. But going off of what IonQ just showed you, right, when I talk to people about quantum computing in the first place, some of the first questions I get are, when will quantum computers replace classical computers? Then I have to do a little course correction. I go, okay, they're not going to replace, right? They're going to work alongside classical computers. So I like to tell people, even though it's called quantum computing, don't think about it like a computer. Think about it more like a coprocessor, right? There's going to be lots of different coprocessors being developed. IonQ's developing them. IBM's developing them. QEra. There's plenty of companies developing these coprocessors. But at the end of the day, they're going to work alongside the rest of the HPC stack, alongside your CPUs and GPUs. And they're going to be good for certain tasks and terrible at others. So you have to figure out where to use a quantum computer, where these new processing chips are applicable, in the same way that you wouldn't run everything on a GPU. That just wouldn't make sense. But there's applications for a GPU that make absolute sense, and you wouldn't want to use a CPU for it. That's essentially what we're doing in quantum computing, a new chip architecture that's going to fundamentally enable a lot of new applications, which is why people are getting quite excited. Now, another very big reason people are getting excited is a lot of these consulting firms, McKinsey, Boston Consulting Report, are all saying that there's between $1 and $2 trillion in end-user economic revenue by 2035, with some revenue available within 2025, 2030 region as well. So we know that quantum computing is going to be bringing end users money. That's not the people in quantum computing. That's not IonQ. That's not Classiq. That's people who are using the technology to develop solutions to bring that to their clients. And some of the top industries, like IonQ was discussing, to see that first kind of use cases for quantum are going to be finance, travel and logistics, chemicals, pharmaceuticals, and automotive industry. And another interesting thing about quantum computing are the promises kept. I haven't been part of a technology or innovation field that actually kept to its roadmaps. So if you look at IBM's roadmap here, they put out the first quantum chip on the cloud. It was about 5 bits in 2016. And all these green check marks are all the promises they actually kept. When they said they'd get hardware out by a certain year, they actually did it, which is phenomenal, especially for a technology so kind of advanced as quantum computing. So there's trust built in the ecosystem. So when they say that by this 2029 timeframe, that they're going to have a fault-tolerant, error-corrected system, they've built up the social equity so we can trust them, right? If they've kept their promises so far, chances are they're going to continue keeping their promises, and this hardware actually will come to fruition. In 2029, we'll have these 200 fully error-corrected qubits. But they're not the only ones in the industry, right? IonQ, who just presented, is trying to do the same thing, and they're also showcasing that by, got to point us in the right direction, by 2029, they're going to have, my clicker works for me, commercially viable quantum computing as well, right? With error-corrected qubits. So they're saying 200,000 physical qubits with 8,000 logical qubits, so the error-corrected bits with this amount of error. So a lot of these hardware companies are saying that they're going to have commercially relevant quantum computers by 2029. The question then is, are companies ready to make use of this hardware? All right. So, like I just said, right, by 2029, we'll have access to hardware with hundreds to thousands of logical qubits and hundreds of thousands of physical qubits. So in 2016, 5 qubits, sure, I can do that by hand. I can code at this low level, create a quantum circuit. Today we have access to computers with about 100 bits. Okay, getting a little bit more difficult. Takes me a little bit longer to be doing this with the current formalisms of coding that we have. But by 2029, when you have thousands of qubits, and by 2030, when we're starting to get to millions of qubits, how do you program for that? How do you actually scale up the design of quantum algorithms, the production of quantum algorithms, so you can take advantage of the hardware that's coming? All right, so what I like to say is don't miss the quantum bus, right? It takes time to build the capabilities. The digital transformation roadmap is not a short one with quantum. I used to work for Kodak, and it took them quite a while to update Microsoft. If it takes you that long to do a simple update of infrastructure, quantum computing is not going to be faster than that, right? There's a lot that goes into a full digital transformation. So, hardware vendors are giving us these timetables when they're going to have relevant hardware. You need to figure out when will quantum computing matter for your corporation and make sure that you're ready for that hardware, right? We have the timetables for the bus. Will you be at the bus stop when it's time to take advantage of it? So hardware really isn't the barrier. We know when the hardware is coming. It's our ability to develop these algorithms, these applications, and make use of the hardware. So how do you actually develop these quantum programs? Now, as IonQ showed before, it looks a little bit like electronic design and a little bit like a Boolean logic and assembly level language. Right, you have truth tables. Here's a XOR argument. Here's essentially a quantum XOR argument. You have your inputs, you have your outputs. So you could think about them analogously in this kind of way when it comes to low-level formalisms and programming. And when you see something like this, what this is a visual representation of the quantum code. Each of these lines is a quantum bit that you're performing an operation on. Each of these blocks is the Boolean equivalent of a Boolean operation on that qubit. So here we have a 6-qubit quantum circuit because it starts off with 0 to 5, and we're performing some operations on it. Oh, there we go. All right, so with this low-level formalism, what happens most of the time when you learn coding at this level, when you're designing code, and when you move forward with this kind of coding, you end up building toy models. Right, you're rotating the block sphere. You can see the vectors and the positions of what your solution should look like. You end up building small, maybe proof of concepts, but you don't get to large-scale applications. Nothing built at this level looks like anything you would use in production. Right? It's not a GUI. It's nothing you can turn into that. It's not variable-level programming. And it requires deep expertise in the quantum hardware. There's lots of different vendors in this industry, too, so you have to learn their vendor-specific languages. Right? Microsoft has Q#, Qiskit has, IBM has Qiskit, Google has Cirq. There's multiple end hardware languages to learn, too, to take advantage of all these different hardwares. And yeah, it's coding out for this. If you wanted to migrate from one to the other, if you wanted to scale up your quantum application, you'd have to really fundamentally start from building blocks and build your entire algorithm again from scratch, because hardware vendors have different ways the qubits interact with each other, right? IBM's hardware kind of works in a ring structure, so qubit 1 doesn't always talk to qubit 5, and you have to be aware of that when you're programming. IonQ, it's all-to-all connected, so you don't have that consideration. But there's other things. They have different gate sets. So which Boolean operations are available on one hardware vendor versus another, and how does that affect which algorithms in quantum computing are more efficient for what you're trying to compute? And as a quick example, this equation, right, y equals 2x squared minus 5x plus 3, this is the circuit that deploys that. And it shows that even for a very simple mathematical expression, it takes quite a bit of knowledge to program something like that out. This can be quite intimidating for a computer scientist, for a developer to see that and want to get into this field. So what Classiq is doing is we've developed an end-to-end software development platform to lower the barrier to entry, make it much more like computer science, and enable developers and corporations to build out their quantum software engineering practice. And at the end of the day, with the software platform we've developed, and what higher level languages in general and formalisms in general allow you to do, is to develop faster, right? Target any hardware vendor, because at the end of the day, we're not sure which of these hardware vendors is going to win this quantum race, and no corporation wants to be found having had put all the development efforts in one corporation when another one is the one that hardware is going to move forward. You've lost your entire code base. But it also enables you to scale your quantum algorithms, debug them, and maintain them for future hardware that comes out. So at Classiq, we've built the first quantum operating system that'll take a user from modeling your quantum algorithm, compiling that quantum algorithm, visualizing, debugging it, and then, of course, executing, and we're connected to most every one of the quantum cloud vendors out there. So what makes Classiq different than some of these other programming languages you might see out there? Essentially, we built out our own modeling language and our own compiler from scratch. And the methodology around this was based off of proven methods in the past, right? We're not reinventing the wheel. We're standing on the shoulders of giants. When FPGAs were coming out, people were coding this by hand. It was awful and tedious. Then high-level dynamic languages came out that modeled the algorithmic intent of the FPGA, and then it compiled out the circuitry. We've essentially done the same exact thing for quantum computing. Our language QMod is a modeling language. You describe the functional intent of your circuit, and then it compiles out the architecture for that quantum circuit. And in our language, I'll go over this quickly to not get into too much detail. We enable a number of different ways to input data, because everybody has different ways to play with data, to input data, and work with it. But it's the flexibility that enables developers to do what they want to do in quantum computing easily and seamlessly. So you can encode data as a qubit itself if you're dealing with the fundamental particles. You can put in quantum numbers and just say, I have an integer, or I have some mathematical expression I want to do. And notably, with our platform too, it's, again, much more like higher level languages. And some of these things tend to get taken for granted in higher level languages like C++ or Python. We're not having to bin out or call out how many bits I need to pre-allocate per variable like you would in most other of these quantum programming languages. You'd have to say, I'm allocating 5 qubits to variable A and 6 qubits to variable B, and I need 10 for my results because I know it's going to take 10. With Classiq, we have automatic inference. It can analyze and understand how many bits should be allocated for the results of your solution. If I'm plugging in the integer 5, it knows that's a 3-bit number, and it's going to assign that for you without you having to be an expert at how many bits I should allocate for the data input I'm using. We can also input arrays of data, and we also have larger quantum structures where you can start putting in multiple quantum types, even classical and quantum types in the same place, and this starts building out the formalisms for object-oriented programming. We also have things that huge quality of life improvements like for loops in quantum computing, where you can take repeat structures, control structures, power structures, making it, again, much more analogous to classical programming in the way that a computer scientist is used to working in. And a great paper by the University of Illinois Urbana-Champaign came out not too long ago comparing multiple quantum programming languages against each other. They compared Cirq, which is Google's language, Q#, which is Microsoft's, Qiskit, which is IBM, a couple of other open source software, and QMod, our language, showing that we're the more efficient language in effort of coding, difficulty of coding, lines of code to actually compute what you're trying to do. So if you're trying to do something in quantum computing, whether it's Classiq or another platform or other languages, higher level languages are what enable you to more seamlessly program out quantum algorithms. You need abstraction in this industry. It's a need, not a want. In the same way that we didn't keep programming in Boolean logic forever, right? I'd hate to build a web page in Boolean logic. Maybe somebody can. Even a hello world would take months to build out that far. It doesn't make sense, even for an expert to do that. You use higher level languages. You use HTML. It's what enables the ecosystem. It's what enabled classical computing, and it's what's going to enable quantum computing. But I personally just love this quote from the paper that our language stands out for its concise and declarative syntax, which enables the expression of complex logic using compact functional constructs. Essentially, we make it easier to perform what you're trying to do in quantum computing. And that's our language. It has to go hand in hand with the actual compilation of the quantum circuit. And the methodology and kind of the thought process around this is that when you run on most hardware vendors or other programming languages, you will encode some solution, right? And you get a result, right? This is the problem I solved. Here's my quantum circuit, my quantum algorithm. It uses 10 bits, and it has a code length of 27 time steps. When that hits the hardware, it'll do some transpilation. It'll migrate a little bit, maybe try and do some cancellation or some efficiencies in that hardware. And you'll look at a little bit larger of a solution space of what's available. But fundamentally, when you're programming at low-level architectures, you're looking at a hard-coded implementation. What we wanted to do is true compilation, right? From a high-level architecture, look at a larger solution space, and then pick out which of these is the optimal solution. And it might be that this solution with 7 bits and 52 depth is the optimal for time to compilation, right? How long it actually takes to compile the code. But maybe you're looking at other solutions. Maybe you want to reduce a certain resource that's expensive to run. Maybe you're trying to minimize just the cost of running on an IonQ machine or an IBM machine. But there's multiple best solutions depending on what you're trying to optimize. And knowing how to migrate your code between these, how do I reuse auxiliary bits? How do I choose different algorithmic functionality is what makes quantum computing so intimidating, right? The breadth of knowledge you have to have means that right now in quantum computing, it typically means you have to be both a computer scientist in this industry as well as an electrical engineer in this industry. You have to understand both the software and the hardware, and that's the intimidation factor, and that's what Classiq is trying to essentially reduce. We're trying to make it so you can only have to be the computer science side. We're optimizing the electrical engineering side so you can focus on the algorithms, what you're trying to develop, what you're trying to deploy within your enterprise, or if you're trying to teach in academia as well. A lot of university lectures will have a Qiskit course or things like this, and we help universities to have that more applied secondary course with a teaching assistant where you can actually start programming out some larger scale applications that industry is looking for. And I won't go too far into this, but for those on the academic side who's interested in how we actually compile all this stuff, it's a giant constraint satisfaction problem on our back end to get you the most efficient quantum code possible. We look at every implementation possibility, how many qubits it uses, how many qubits it might release at different parts of the algorithm, and essentially we'll go ahead and looking at your global constraint, we make local decisions on which implementation pathway makes most sense for your algorithm and your application at large. Now, there's a lot of decisions that come into this when you're programming a quantum computer, and some of the things that Classiq helps enable and simplify, right? What are the multiple different implementation pathways that you can take? Memory management, should I reuse qubits? Should I use an auxiliary bit? If I'm using an auxiliary bit, how do I clean it up and use it later in the algorithm? And uncomputation methods. So This one's interesting. For those in computer science, one of the major differences between classical and quantum programming is essentially, at a high level, when you program something in a quantum computer, you have to unprogram it. So there's multiple interesting ways to even do that efficiently, and our system handles that for you. And again, all these decisions are made locally, but considering the global resource you're trying to optimize. Maybe you're trying to run on the IonQ hardware you have on site that has a maximum number of bits allowable to it. So you say, don't return a quantum circuit that uses more than this, and optimize for a particular hardware set, and it'll go ahead and compile, considering all these different optimization schemes, what's the best implementation given that set of constraints. So going quickly through this, for those who are in quantum computing, there's something called a multi-control NOT gate. This is one that's looking at 10 controls and one target. There's multiple ways to implement this quantum circuit, right? You can do it with 11 qubits, you can do it with 14 qubits, you can do it with 15 qubits, and each of them has a different circuit depth. And it's important to know that they have a different circuit depth, because the longer your quantum algorithm has to survive for, the noisier your solution is. So the tighter you can get your quantum circuit, the better your signal-to-noise ratio is on current quantum hardware. So there's multiple implementation paths. How do you, switch between these? Which one's the most efficient for the hardware you're looking at? Again, are some of the things Classiq optimizes for. Things like I said, memory management. Here's a quantum algorithm where I'm doing an addition of A plus B and B plus C here. I can do them in parallel with 15 qubits and a 72 depth. Or I can split them up in time and do A plus B and then C plus D. It uses one more bit, but it cuts down on that depth significantly. And as a practitioner, a user of this platform, I know what I want the quantum algorithm to do. I want it to do this addition, right? I let the system figure out which of these implementation pathways is the most efficient for what I'm trying to do. I don't have to be an expert at all these low-level optimization schemes. And then, of course, there's that uncomputation method, which gets tricky even for experts. You can, of course, take a full circuit like this, and you can execute it a slightly different way as well. The top one is computing everything and then uncomputing everything. Kind of a brute force method, but you can also take a little bit more sophisticated pathway, uses fewer qubits if you need to squeeze an algorithm into a smaller bit of hardware. Takes more depth, but that might be the difference between being able to run an algorithm versus not being able to run an algorithm. You can speed up the time scale on when you can run quantum hardware by having these efficiencies and by able to essentially squeeze your algorithm into a smaller number of qubits, enabling you to actually run larger, sophisticated quantum applications. So in this lower one, we're actually computing and uncomputing a small part of the calculation, recomputing part of it, and uncomputing it, and recomputing and uncomputing and computing and uncomputing parts of the algorithm at different times. So there's a couple of different ways to even do uncomputation when it comes to quantum programming. And what all these optimizations, what all these considerations mean is that users of our platform end up seeing tremendous cost savings when it comes to the size of the quantum algorithms they're deploying, right? Higher level languages mean that you're looking through a larger space of solutions than any one individual programmer can when you're doing low level coding. Even if you're a quantum expert, you're gonna focus on one application, you're gonna develop one application, and that's the application you're gonna run on. Maybe you're trying to optimize that. But computers are good at looking at multiple solutions, and that's what we're doing with Classiq. With Classiq, we're able to find upwards of 90% reduction on the number of the C0 gates, which is a 2-qubit gate, which ends up both being the more expensive gate on quantum computers when you actually look at how much it costs to run on them, but also the type of architecture and gate that costs more money as well. So it adds error and it costs more money at the same time. Also with the depth of that circuit as well, we're able to compact that. So we're looking at this. These are all 3 independent use cases, all blogs from our clients. These aren't benchmarks of ours. These are blogs or papers that our clients have put out of their own volition, showing that Mitsubishi Chemicals was able to save 97% of reduction in depth compared to the tools they were using. Mizuho and Sumitomo, who were looking at Monte Carlo algorithms, were able to save 94% reduction in their depth. SoftBank did an evaluation in Classiq and was able to save 90%. They were doing chemical simulations of H2 and evaluating very particularly an algorithm called quantum phase estimation. But they were able to see huge savings versus Qiskit and TQEC, which is TQEC's Quantinuum's hardware language. So that's the language, our compiler, and then we add a lot of other things to make the life of quantum developers easier. We have a visualization tool, so you can go ahead and analyze the code that gets compiled out for you, right? You actually want to see it, review it. A lot of universities use this for education, so you can dynamically view not just the individual gates themselves, but we block and code them into larger sections, so you can follow the algorithmic intent of the quantum circuit. You can follow your variables. It makes it easier to analyze your code, makes it easier to debug your code. As IonQ was talking about before, there's a consideration when you're programming these systems that you have to look into is the phase. You can always say, ooh, I'm getting a phase I wasn't expecting in my quantum solution out of this variable. You can always backtrack that through this logic and see where did that phase come through, what algorithms did that variable flow through that may have contributed to that. So having these visualization tools is also incredibly helpful, not just for education, but for debugging. And then when it comes to execution, we're connected again to most of the major hardware vendors out there, and we'll digest out the quantum solution for you, so you don't have to figure out what this binary string, 10001 means. We give you the solution in human readable text, right? A equals 1, B equals 0, and C equals 2 is the solution to the result of the calculation we were looking at. So a lot of times looking at these histograms of solutions is something that computer scientists aren't used to looking at, right? They're used to getting a solution. They're used to seeing things already pre-digested for them. And we're doing the same thing in quantum computing. We're digesting that for them based on the algorithm they're putting in, which is why it's important when you program it out, you have to say what your solution is that you're looking for so we can properly digest that answer and give you that solution. Another one that ends up being an issue, not for this bit string because it's symmetrical back and forth, but different hardware vendors, when you load the data back out, there's not a lot of consistency in this industry since there's so many different hardware vendors out there. Sometimes you need to read the bit string from that hardware forwards, and sometimes you have to read the bit string backwards depending on the hardware vendor you're looking at. So I've had a lot of very confused graduate students come to me before saying, my data looks like it's completely nonsense. It's all, oh, no, you're working with that hardware vendor. So you got to flip the bit string and then it makes sense for you, I promise. It's just, there's a lack of kind of consistency in the ecosystem, and that's another thing that Classiq will handle and make sure that's not a problem for users. A lot of these kind of low-level bits that cause confusion, what are the API calls for all these different hardware vendors, we make it a simple drop-down menu. You can go ahead and select out, I want to use IonQ, or I want to use the Anka machine on Amazon, or Rigetti on the AWS or on the Microsoft system. So trying to simplify out the complexities of quantum computing wherever we can find it. And because we know that nobody learns how to program by reading a manual front to back, right? You try and find a code example that looks similar to what you want to accomplish, and then realistically, you learn as little as possible in that documentation to actually get you the rest of the way to program out your application. We have the largest open source quantum library on the internet, so you can look at applications that are similar to what you want to do. We kind of have it split up between two major algorithm folders, two major folders, one on algorithms and one on applications. Because those in academia want to see what are all the algorithms that you can deploy and algorithms that I'm wanting to investigate, and those in industry want to see applications in their industry and ecosystem. And whenever we work with a client, if we do some project with them, we always ask at the end of it if they're okay if we publish some small toy model version of it on our GitHub to help support the community at large. And another important one too is our code library on Qiskit is backwards compatible and constantly updated. So you're never going to find code on our GitHub that won't run, because as a user of software in the past, that's always my most frustrating experience, is I found an application online that is exactly what I needed it to do, and it doesn't work because the application is updated and that code notebook wasn't updated with the software. And I am just left so sad. So we update our code library whenever the software updates, so you're never going to find a notebook that won't actually run. And because quantum computing can be a bit intimidating, and because we have the largest open source library on the internet, we train that open source library with a code assistant. We plugged in Claude to that open source library, and you're able to essentially get realistically 95% of the way to a full solution working. Sometimes you can get it running right off the bat with one code input, but sometimes you have to tweak some code, right? AI isn't completely there coding everything for us, but it gets you a significant amount of the way so that it's helped out me tremendously working with clients. It's helped our clients move forward and develop the applications they want to look into. And actually, I'll show a quick video here of our AI assistant working on a financial algorithm. So in this video, we're looking at some insurance algorithm. We're going to show the quantum circuit that this algorithm uses in this paper. Then we're going to, I don't know why they use Google, but they Google Classiq to get to our homepage. They go into our website, and this is the prompt, right? Here's the paper, generate a quantum circuit that solves the problem using Classiq library. And they clicked enter. And this is the code that got generated out. So it's going to ask, can I actually read that paper online? You give it permission. And it's going to start coding out. And the cool thing about Claude and the way it works out, too, is that it'll look through what it compiles out. And we've told it to go through a couple of iterations. If the code won't actually run, it'll see the error code and try and fix that before telling you it's done. So it'll go through a couple of loops before it gives you a full solution out. But the cool thing is this code ran without any edits needed afterwards. It was a really great example, which is why we like showing a video of it. And this academic paper, here's all the code that Claude ended up generating for us, trained off our library. And if you click that, you can see the full algorithm. It's going to look exactly the same as the academic paper here. So it replicated the circuit in that academic paper. And if you look at the solutions out here, it actually goes ahead and replicates the solutions of the paper as well. So they validated the paper is correct. They were able to reproduce it internally for validation purposes. And this is tremendously helpful because that tends to be the first thing a lot of clients and enterprise users want to do. They see something very cool on academia or some blog, and they want to replicate that for themselves. And this is a great tool to get you most of the way there of the coding to replicate that exact solution so you can see it and actually code that out for yourself and then build upon it. And Classiq, we not only have this quantum software engineering platform, but we're also happy to work with clients wherever they are in their quantum journey. A lot of clients need help on the education side where they need just, what is a qubit? When does it matter for my corporation? Why should I be looking into quantum computing? Building up their capabilities. Some clients are Qiskit experts, have been doing this for a long time, and now they're bumping their heads against the wall trying to build out larger, more sophisticated algorithms, and we'll scale up their ability to do that from there. And we'll also do co-development for certain more sophisticated quantum projects. If there's something novel you want to do or interesting, we're happy to have our developers work with your developers to make sure that happens. But quite specifically, our company is very much teach a person to fish. We're not just going to make code for you and hand it to you. We want to make sure that you are quantum competent by the end of any engagement with us. Also, because fundamentally we're a SaaS platform. We want you to be able to use the tool and be able to move forward with any applications you want to do in-house after our engagement. We want to make sure that you leave working with us a quantum expert. And we've done this with quite a few clients. We worked with BMW doing some interesting kind of unit commitment problems on their systems, HSBC on fraud detection, Toshiba on machine learning, Rolls-Royce, we were doing some fluid dynamic calculations that will eventually go into digital twin simulations. Comcast was a fun, more recent one on telecom network resiliency. Applications from every industry, every application, and actually that's actually what makes quantum computing so interesting and fun on an employee side to work on. You're working with many different clients, many different industries, many different use cases and problems. It makes it very fun and dynamic ecosystem to be part of. And in helping build out these capabilities, we've worked with Intesa Sanpaolo, Italy's largest bank, and one of the largest banks in Europe, build out their quantum capabilities. We started in 2023, building out their quantum team from scratch. And I think not too long ago, we won second best paper at IEEE. IonQ beat us out for the best paper. But now they're going and doing independent quantum research on their own without any further assistance from us. Comcast had a great team of AI experts looking into quantum computing already. And their corporation saw quantum as a thing to do after AI, so they had their AI team work on this. We trained them up on how to use our platform. It was just 2 days of product training. In 3 months, we did a joint project where we submitted a paper actually working with AMD's GPUs to do a hybrid workload job for network resiliency. And then after that project, they had something to show the board of directors, their managers, and then we deployed quantum education larger to the rest of their Comcast ecosystem to get them on board to see where the capabilities of quantum computing are and where you can utilize this quantum capability, because quantum computing will apply to every quantum industry, sorry, every industry out there, every vertical. It's just a matter of figuring out when will it matter for that vertical, what problems should we look at first. And that's a lot of what we end up working with the client first on, how to identify these problems so that then we can work in the platform and develop the solutions. So with that in mind, I wanted to have in here a little bit of some of that framework, some of what we do with clients to help them get started on how do you become quantum ready. So when I work with clients, I like to always say that there's 3 bits to being quantum ready, right? There's technical readiness. You have to be able to understand quantum computing, where it applies, where it won't apply, how does it scale, right? As IonQ showed, it scales up quite phenomenally quickly, but certain applications need more bits than others. What's the transition point between classical and quantum, and when will quantum be better for your application? There's strategic alignment, right? You need to focus your investment, your business goals, and long-term goals with what's actually happening in application. And then there's, on the organizational side, you need to make sure that you have the skills, the governance, and the cultural support to enable these quantum advancements. If you want quantum to affect your entire industry, your entire ecosystem, all your divisions, you need that governance and organizational support to be there. So one of the first things, I'd like to kind of put this into a 4 or 5 step program at a very high level. The first one is to map out where quantum computing matters for you, right? Triage the different areas that are computationally intensive in your industry or business unit, and then figure out when will that quantum application matter, right? It's a matter of looking at the time to impact and strategic value. So you need to first figure out for the kind of problem I'm looking at. Maybe it's a graph theory problem. Maybe I'm looking at a Monte Carlo kind of problem. There's a lot of great resources out there. There's companies like myself. There's others out there that'll help you also figure some of these things out. A quick gut check of which are the longer-term applications and shorter-term applications for quantum, right? High-frequency trading is not something that's going to happen anytime soon. We need larger hardware. We need them to be faster to do high-frequency trading. So it is an application, not in the near future. So push that one out, right? Maybe you look at smaller-scale optimization algorithms, maybe some interesting machine learning algorithms. If you're fine-tuning certain parameters, there's some near-term applications there. So you need to triage where quantum opportunities are for your business. Yeah, so the goal here is to realize the opportunity, not just, I think this is cool. A lot of times people come to us because they saw something cool or interesting that they want to do, and we have to do a little course correction and say that's absolutely a really great application for quantum, but that news article, which was talking all about the quantum hype on weather forecasting and these large-scale things, is a much further application. We can talk to you about what more, some of the more near-term applications, so you can get that, build that out, have, reasonable ROI on this investment into quantum computing, and then you'll be ready for the longer-term applications of quantum. But let's talk about what's a little nearer term than the thing you came to us in the first place. Second part is this benchmarking of performance. You have to figure out from that triage list, when is that transition point for when quantum matters, and when quantum will be either a financially easier solution or a computationally easier solution, right? When is it going to be advantageous? So you have to look at what the time is that you're okay for this calculation to take, and how large a problem is you're looking at. So it depends on what you need. Do I need a solution fast? Do I need a large solution? Once you have that paradigm figured out, I'm okay with a solution maybe taking a week longer than what I'm currently using. Okay, that's great. Let's look at the data size. Let's compute this out. Let's see how the algorithm you're looking at scales with larger data input. And now I can see that IonQ says they'll have hardware that'll be able to run that algorithm that's going to take that many bits by this year. Now you have a quantum finish line. Now you know when quantum will matter for that particular application. And there's no one answer to that. People always ask, well, when will quantum happen? Oh, it depends on your business, it depends on your use case. In the same way that classical computing evolved, it was a banking tool initially, right? And as the hardware got larger, more applications became feasible, more applications became available, and it branched out from there. Same thing's going to happen for quantum. It's going to apply for a couple of different problems and use cases. As the hardware scales, more use cases become available, more use cases become advantageous to actually move over to a QPU than you would on a CPU. So you need to determine when that switch over is for your business unit so you can start building out the IT stack to make sure you're there. Next is figuring out that whole IT stack, right? It's not just I built an algorithm, done. No, right? You have to figure out the application layer, the quantum layer, right? What quantum platform you're going to be using, the hardware vendor you want to work on. Do you want an on-prem system, a cloud system? Which one of them do you want? For the application you're looking at, maybe IonQ is better than an IBM or a Rigetti machine, but you need to actually do the investigation if you're going to be putting that kind of investment in. And then there's things that rarely get actually talked about in quantum computing, which is the security and compliance aspect. If you're doing anything that's going to be customer-facing, does your algorithms, does your computation stack meet SOC 2 security protocols, MSA agreements, any kind of data governance that might apply for the solution you're looking at? Right, energy sectors and other sectors are more data, have more of that governance they have to worry about. So essentially making sure that you have the technical feasibility and deployment side ready for quantum, because you can't just tell your IT team, begin, right? That's not how this is going to work. They need the time to build out all this stack. It's not going to be a trivial thing to switch over something you've been doing in your corporation from classical to quantum. If you want it to be a seamless integration and a seamless switchover, you need to build that seamlessness in, and you need to be ready for when the hardware arrives. And the last one, right, is embedding the quantum capability across your enterprise, right? What's your IP strategy, right? If you're developing intellectual property, you can't patent code, but you can patent a novel implementation pathway or novel series of operations. And a lot of companies right now, you can look at one key example is JP Morgan. They're publishing quantum patents for their classical core competencies, right? What they have patents for classically, now they're patenting the quantum analog thereof to make sure that they're protected in the IP space. And they're doing an interesting strategy where they're publishing IP, and then they're also publishing academic papers to kind of make it even harder to get close to their core competency, because now it's all public. So you need to figure out what strategy is that for you. Do you want to develop a similar strategy? Are there any core competencies that have a quantum analog that you need to start protecting and looking into? There's internal innovation programs in education and knowledge transfer. How do you, beyond having a team that knows how to do this and work on it and look at it, how do you transfer this knowledge to the rest of your businesses and divisions, right? Like at Comcast, we were working with their AI and data team. Well, quantum computing also matters for the finance team. It also matters for the logistics team. They need to start looking into where quantum will matter, start triaging the applications that they'd want to use quantum for, and start investigating that. They might not be the ones who build the programs at the end of the day, but they need to know the kinds of problems to look into for whoever is programming these solutions and looking into it to actually build this out. Because you need the field experts, right? The AI team will not have as much knowledge in fintech than your finance team and all the algorithms and all the eccentricities of the data they're dealing with. You need, essentially, you need these experts to be part of these discussions to understand enough about quantum to figure out where might it be interesting to apply, how can I deploy this, and for them to have some kind of rough estimate on when it will apply for their different business units. So really moving that from this experimentation phase to real enterprise-wide strategic capability. So quantum readiness is not about running a pilot and being done. Oh, I did it. I put out a bit of PR and I'm good. It's about identifying when quantum becomes useful, preparing infrastructure for that moment in time, and building the institutional capability to capitalize on that. So we know when the hardware is coming, right? It's no illusion. The hardware vendors are telling us exactly when they're going to have hardware, by what dates. They've kept their promises. We know this. Are you ready and have the applications and capability to make use of that hardware? Because it takes time, right? So it's not that the hardware is the barrier that's limiting us. It's our ability to build applications and make use of the hardware when it's here. All right, thank you very much.